So I'll be talking to you today about some simulation work I've been doing recently on the optical gain effect for and the implications for the harmony HSCAO pyramid wavefront sensor. So as we already had the very nice talk by Enrico, I don't need to spend too much time on the introduction of optical gain. But just to recap, the optical gains really refer to the difference in sensitivity between the calibration state, where we're typically using the diffracted limited PSF, and the operating state where we have the AO corrected PSF. And so this we call sort of a reduction in optical gain. So there's this mismatch between the calibration and the on-sky response. So if you use your calibrated command matrix, you'll be underestimating your wavefront. So if you see the plot here, this is an example of the optical gains for different KL modes, for example. So so what we want to know basically is, okay, we can, if we have knowledge of the optical gains, and in this case, we're looking at the modal optical gains, we can then correct our command matrix to more accurately measure the wavefront. So the approach that we're taking for harmony is we want to use the convolutive model. So this was developed by people at LAM. So I would recommend that you read this paper, which will give you more details on it. But just to give you a kind of brief overview, this model basically, it estimates the linear part of the wavefront sensor signal, so this meta intensity, as a convolution between the phase and the impulse response. So the impulse response is a function of the sort of the Fourier mask of the pyramid wavefront sensor, and then a focal plane weighting, and that incorporates the PSF and the modulation. So in the case of the calibrated, so our calibration case where we're using the diffraction limited PSF, the weighting function would be like this. And in the operation case, we would have a PSF like this. A weighting function like this. And so using this model, we can compute the response in calibration and on sky if we have some knowledge of what the PSF looks like, the on-sky PSF. And so we can compare those two responses, and basically from that we can extract the modal optical gains. So the first thing I wanted to do for, or we wanted to do for harmony, was to get an idea of actually how much of an impact the optical gains have. So we did some simulations over a range of different seeings. So in the first case, so you have these two dotted lines. So that's the performance with no optical gain compensation. And the red and the blue are for two different wind speeds. Now the solid line is basically compensating for the optical gain using the convolutive model. And in this case, we're using the full knowledge of the residual phase that we have from the simulation. So it's just to show the kind of impact if we could fully compensate for the optical gains using this model. So you can see, obviously, when we compensate for the optical gains, the performance is better. And if you see this plot down here just shows the quadratic difference between compensating for optical gains versus not compensating. And so as we expect, the worse seeing, the more of an impact the optical gain has on the performance. And so that's just to give an idea of the impact of the optical gains, but of course, in practice, we don't have full knowledge of the residual phase. Ideally, if we had a camera in a nearby focal plane, we could feed the convolutive model with the actual PSF, but this is not an option for harmony. So we've been looking at an alternative approach where we use a reconstructed PSF. and particularly how much knowledge we would need to have of the system. So what I've been looking at is just using the fitting error. And so some very recent results that I've simulated, so using that reconstructed PSF as shown here. So it's for one particular case for a seeing of around an arc second and a wind speed of 5.5 meters per second. And basically what's shown here is you have, so this dashed line here is the result we get when we do the optical gain compensation with perfect knowledge of the PSF. The solid line is with no optical gain compensation, and then the blue line is with this reconstructed PSF. And that's using different values for R0. So basically, how accurate do we have to be in our estimation of R0 to get a good compensation with this model. So you can see that, you know, we kind of get close, or we get to the same result as with the true PSF, and get very close to that for if we have positive errors of R0, up to 30% I've simulated so far. If we kind of underestimate R0, basically what happens in that case is you're going to underestimate the optical gain and overcompensate for it. So in this region here, you're basically seeing a buildup of errors because we're overcompensating for the optical gain, and in particular you see a buildup of some high spatial frequencies. So yeah, this is ongoing work, so I need to do several more simulations, of course, of different cases, but this looks promising, at least in terms of there's a kind of wide range of R0 values that still give us relatively good optical gain compensation. And thank you.
Thank you.
Questions?
Yeah, thank you, Charlotte. So I don't know if there are no questions yet. So I encourage people to post their questions on the Slack. A question by Miska maybe: does the R0 estimation assumes the L0 is known?
Well, so it's for an infinite outer scale.
Okay. Well, thank you very much. So thank you for this nice talk.